This is where we left off on the last part, and we were trying to explain what holds these covalent bonds together. In this concept, I guess we went into a little bit about this concept of electronegativity. Um, it's how much that particular element wants to hold on to its electrons, or how much it is willing to share its electrons. Let's put it that way, particularly in the fact of covalent bonds. And in terms of water molecule, which we consider a polar compound, the opposite being the non-polar compound, which would be a hydrogen compounds, where hydrogen has an equal electronegativity, so has an equal attraction for the electron that's being shared. With water, which is polar, the electrons spend more time around the oxygen portion of the compound than the hydrogen. Just based on size, you can see this image, oxygen is much larger than the hydrogens, but it also has a stronger pull for that electron, so it has a stronger electronegativity. And that makes it polar. It makes it have a portion of that compound that will have a negative charge and a portion that will have a positive charge. It becomes very important in the next chapter when we talk about water and the properties of water and why water is so important for life. This unequal sharing is what causes this polarity in a compound that we're looking at. The second type, remember there's three types of bonds: covalent, which we just talked about a little bit. Second one is ionic bonds, and that's IONIC, ionic bonds. With them, the most common example is sodium chloride, or otherwise known as table salt. If you think of table salt, it's a solid in your salt shaker, or however you get your salt in your salt packet. And then when you pour it in water and you stir it, it's all gone. It disassociates. So ionic bonds are formed when there's a element, in this case it's sodium, who actually loses an electron and gives it over to chloride. And I think I have a typo there. It's chloride on both of them. It's not chlorine. Chlorine is not what that first one says, sodium atom and then chlorine atom. It's supposed to be chloride. It gives that electron over to the chloride atom, so basically it loses an electron. It then has a positive charge because it's deficient in one electron, and the chloride element then has a negative charge because it has one extra one. So you have a unequal sharing, or no sharing, whichever way you want to think about it, where one electron is transferred over to another element, and then you have a unequal sharing, which creates this charge we call an ion. An ion is either positively or negatively charged. So if it is positively charged, we call it a cation. If it's negatively charged, we call it an anion. So cation positive, negatively charged anion. And the thing about this particular compound, they are attracted to each other because really that electron belongs to the other. So the electron that was given to chloride belongs to the sodium. So they're attracted to each other, but not particularly very strong. That attraction isn't the strongest. It would disassociate in water, as I said. If there's no water, if you take the water out, so you dehydrate salt, take the water out, that attraction then would hold that bond together in a solid. So ionic bonds, unequal sharing, one will donate electron to the other, and in that donation you have positively and negatively charged ions. Positively charged is a cation, negatively charged is an anion. An example is table salt. The third type of bonding, remember covalent, ionic, now we have hydrogen bonding. And this becomes important in nature because many of the processes that we study are because of these attractions between hydrogen bonds. So when a covalently bonded hydrogen, it's positive, it's attracted to a negative atom, you have these interactions where that hydrogen, which is actually bonded to the oxygen, but remember it has a little bit of a charge, so it's acting a little bit like an ion. It's not an ion, don't get me wrong, it's not an ion, but it's acting a little bit. So if there's something that comes near it that has a negative charge, it's going to be somewhat attracted to that particular compound too. So what you have here is water, your H2O. Remember, you have your molecular formula, then you have your 3D design of it. And because those hydrogens have a slight positive charge, just remember this is covalent bonding, but it's polar, where they're sharing those electrons, but not quite equally. And so that hydrogen then is going to be attracted to something that's negative, and you happen to have a negative charge on this nitrogen, on this ammonia compound, which has nitrogen and then 3 hydrogens. And so you actually have this attraction between, which we call van der Waals attractions. And it's the interaction between molecules that are in close proximity to each other because of this polarity that is set up with a hydrogen, and we call that hydrogen bonding. The last thing we need to talk about are chemical reactions in general. We will describe some chemical reactions, particularly in chapter 4 when we talk about large macromolecules. It's a chemical reaction in terms of cellular respiration and a chemical reaction for photosynthesis. So there are a few chemical reactions we talk about. So just understanding a little bit about what a chemical reaction is, you basically have three stages or three general areas. You have reactants. So those things on, and you're balancing this on either side of an equation. So you can have that reaction arrow, or you can have an equal arrow. Generally, we don't use the equal sign because these reactions can actually all move from the left to the right, or they could be moving from the left to the right in something we call equilibrium. So you have your reactants. Those are the things that are going to be acted on, that you are going to put energy into in some way and cause a bond, whether that bond be covalent or ionic or hydrogen bonds. In this case, it's going to be a covalent bond. We are actually going to create water. So you have 2 hydrogens, they're bonded together, 2 oxygens, and what we have to do is put some energy in there. That can be in the form of heat, or it could be in the form of nuclear or some sort of energy that breaks the bonds that are there. So you break the bond between the hydrogen atoms and between the oxygen elements. Sorry to misuse a word. Well, actually, I'm not misusing it. I just want to be consistent. And that then pushes the reaction to the right. They reform after that energy has dissipated into the hydrogens bonding with the oxygen and then forming 2 water compounds. One of the reasons the hydrogen is going to bond to the oxygen is because the attraction is stronger. There's more of an attraction for those hydrogens than there is for the oxygen, and there's more of an attraction for the oxygens via the hydrogens, so that particular compound is going to be created. Now that happens to be a very stable compound, and so this reaction will move to the right until the energy is used up, and then if you in fact want to move it back to the left in this scenario, you'd have to put more energy back in. But generally the reactions go to the right unless you have two arrows. So where you have that reaction arrow, you're seeing it go from the left to the right. If you had another arrow that went from the right to the left, you would know that this was either a reversible or it's one that is that goes back and forth until equilibrium is met. This particular reaction generally tends to go from the left to the right. So reactions are how we make new compounds. We make them in our body. We break down compounds that we eat, and we remake more of ourselves. The compounds that are the raw material of this chemical reaction are called reactants, those things that are going to be acted on. The reaction takes place, and sometimes you have to have energy sent in, or sometimes there's a cofactor sent in, or some sort of additional input, and then you have the products that are the result of this reaction. That is the end of chapter 2. We will move on to chapter 3.